1, and this is going to be called a directional derivative. Okay, directional derivatives. You see the way I did it on the last time, on the last section. We start with the notion of a tangent line or the derivative of the function of one variable, and we arrive at the fact that the function can be estimated by its tangent line, and that will help us to get the linear approximation, and from there we got the kind of derivative of the function. And I talk about the difficulty that we have when we're dealing with the definition of a derivative. So what we're going to do, we're going to do the same thing again. But this time we are going to motivate the kind of rate of change format of the derivative of the function. Remember, let's see what I'm talking about, the rate of change format that we have from calculus, again, function of one variable. That gives you a nice idea of what we are doing really. That helps to understand it. So again, recall what we did before. Recall that if, let's say, the function y equal to the f of x is going to be, is differentiable, if you like, is going to be differentiable, let's say at something like x equal to the x0, if you like, then the definition that we can use, we call it rate of change format of the derivative of the function, is this one from calculus 1. F prime of 0 is equal to the limit of, okay, rate of change. So we change the x0 into the x0 plus h, if you like. Okay, and this is it, minus f of x0 divided by the difference. The difference between x0 plus h and the x0 would be h, and h goes to 0. This is the version that we call it rate of change version of the, and of course this is f prime of the derivative of the function for function of one variable. Remember when we try to change this formula into the notion of the function of two variables, the difficulty in the previous formula was that we just used the tangent line format. So the denominator was the difference between 2 points in R2 and R3, and that was a vector, and that make it difficult for us. But if you use this version over here, this version, for the rate of change, this h is a number, you know that. For example, if x is 2, you may go with a 2.0205. So since this h is number, so we don't have any difficulty by saying dividing by h. So that would take care of the one that we did before. And for the top, we don't usually have any difficulty on the top because the function is a function of real variable, and then this quotient makes sense. Okay, so what is going to be the two-dimensional, if you like, version for the function of two variables for constructing this formula? Now, let's see what's going to be the difficulty if you want to do it in the two variables one. You see, for the function of a variable, you know that these entries, these inputs must be in the domain of the function. Since the function is a function of one variable, domains are numbers. So x0 plus h is a number, it makes sense. And this makes sense. But if you want to change this one to the function of two variables, for example, this is going to be a vector. Okay, this is going to be a point. It's going to be a vector, if you like. Then this h is a number. Then we'd be in trouble, adding the, that we cannot add the scalar and the vector together. So what we have to do is we have to change this h over here, kind of change it to a vector to be able to do it. So we're going to bring a vector here, and that vector is going to be a nice one, a unit vector. You know that the most popular unit vector is ijk. So you can do those or another unit vector. So the only change that we need is change this h kind of into a vector. So that's why they call it directional derivatives. We're going to find the derivative, but in the direction of a vector that I'm going to pick that makes sense if I add these together. So instead of the h, I am going to use h a scalar multiple of h times a vector. So h times u, if you like, when u is going to be a unit vector. So that's the purpose of this method. So we got this one. Now we can say that, oh, similarly, almost similarly, so what we can do is if the function, okay, if the function, let's say, is z equal to the f of x and y, we can do it for 3-dimensional, of course, okay, is a given, okay, and a point, okay, and a point x is 0, y 0, of course, in the domain of f, in the domain of f is given. I'm going to copy that one. Then what can I do? I can change it to the so-called the directional derivative. The directional derivative. Okay, directional derivative of f at that point, x0, y0. Now I need a vector in the direction, okay, in the direction of anything I like. Yeah, but in that case, in the direction of the, okay, direction of the vector. Okay, in the direction of, I'm sorry, of the vector, let's say u is going to be defined by let's say I just make it into the definition first, is going to be denoted first, denoted by, the definition is that derivative in the direction of u of the function of f at the point of x0, y0, okay, and is defined by, and is defined by, this is it. The definition is going to be, okay, the directional derivative of the f in the direction of the u at the point of the x0, y0 is going to be equal to the limit of, we get this now, h goes to 0 as h goes to 0, no difficulty. H over here as we did over there. Now I'm going to find what? The value of this function. But remember, I have now a function of 2 variables, so I have to go to this one add. This is going to be f of, I change the x0 into the x0 plus, okay, x0 plus plus h. Okay, but remember, x0 plus h, then what I have to do is, I have to bring a vector over here. I put the u1, which is going to be component of this one. Okay, x0 plus h u1, and this is going to be y0 plus h v2 u2. Okay, now minus f of x0 y0. Okay, makes sense. So instead of x0 plus h, I put x0 plus h u1. Okay, and y0 plus h u2. Of course, this is going to be defined by, okay, defined by this. Okay, if the limit exists, and of course, and u equal to u1, u2 is going to be the given, or a given unit vector. Unit vector. It must be a unit vector to be able to know, to be able to do it. Okay, so that makes sense. So exactly, you see, that gives us a nice idea of what's going to be the origin of our argument that we are going to take it. So we just did a modification of that expression on the top. So x0 plus h, now it becomes x0 plus h times u1. u1 is a component of the unit vector of here, is a number. Okay, so this makes sense to get this true here. Okay, and then we get the y0 plus h y2. So these two numbers over here, and everything is nicely done, and it makes sense, and then we'll be able to talk about it. Okay, so quickly you will find out that what is the origin of this argument. Quickly you find out this is the extension of the, okay, it's the extension of the partial derivatives. You see, in particular, if okay, if u is equal to be equal to the I is a unit vector 1 0, okay, which is going to be, this is your u1 and u2. If you go back and substitute over there, what's going to be the result? Okay, so the directional derivative of f in the direction of I at the point x0, y0 would be simply limit of h goes to 0. This would be h. Look at the top. The top now you are going to have it's going to be f of x0 simply plus h, because the u1 is 0, comma, that give you y0 plus h y2, but the u2 is 0. So that give you y0 minus f of x0 y0. Look at this one. The second component is fixed, and you just bring the definition on the first component only. So this means that this directional derivative in the direction of I is simply partial derivative of f respect to the x at the point x0, y0. See? And similarly, if you let your unit vector to be j, you know that the j is going to be 0, 1, and then you pick this one to be u1 and u2, the directional derivative in the direction of the j, f of x0, y0 would be changed to the partial derivative with respect to the y at x0 and y0. Okay, so the directional derivative is in fact the extension of the partial derivatives. Any question? So it's nicely done. And now, of course, if you want to use this limit and find it, it takes times. So what we're going to do is we are going to simplify it. We're going to simplify it, and we find an easy formula to operate. So I'm going to simplify it. We do the same thing as we did with the linearization. Remember, the way we did the other one is we consider this top one and we work on this. Remember, we call this one kind of L of XY, and we checked it. So let's take this out, the top. Everything is constant. You see x0, h1, u1, u2. So this top one would be in fact a function of h on the top, and the bottom is h. So let's go back and look at this formula to see if we want to simplify. Any question? So I'm going to simplify this one for you, and at the end would be very easy result, and then we're going to apply that one. It's nice to do it, nice to see it. Okay, otherwise we can give you the definition right away, but it's nice to work on the top. So let's take that top expression out and to see if there's going to be something interesting. So let's look at it. Note that I want to prove it for you. Note that if the top expression is going to be called g of h, because it is g function of h, g of h, that's the top, f of x0 plus h u1 comma y0 plus h u2, okay, minus, so that let's call this one h, g of h. If you call g of h, then if you replace the h by 0, it's going to be g of 0. You see, if you get the g of 0 here, the result would be what? This is it. It's going to be equal to the You put the h0, that give you f of x 0 plus this would be 0. Okay, and then you get a y0 plus 0. Okay, so that simply give you f of x0 and the y0. Okay, if we go back to that fraction that we did have, so what we have is the directional derivative of f x0 y0 in the direction of u. Now it will be changed to what? It's going to be changed to the limit of h goes to 0. So the top in terms of the g function give you g of h minus g of 0 divided by h. You see? You know that this is simply definition of the derivative of g at 0. So that would be equal to the what? Equal to the g prime of 0. Okay, so that the directional derivative would be g prime of 0. Remember, g is a function of h. Let's go and find g prime of 0. What's going to be g prime of 0? You see, look at this one. You bring this one down and differentiate it respect to the h. So if you want to differentiate respect to the h, look at this one as, you see, this is the function, and this is going to be y0 plus h u2. If you want to differentiate it, you may think about this one as x, okay, and think about this one as y. So you have a kind of f of xy. Now this is going to be where, okay, where just for a while, x is x0 plus h u1, okay, and y is equal to the y0 plus h u2. Now let's differentiate it. Okay, so differentiate everything respect to the h. If you differentiate x, you see respect to the h, dx dh would be u1 because derivative of h u1, and dy dh would be equal to the what? u2. Now differentiate g respect to the h. So what's going to be g prime? G prime of h, you see, is a function of two variables. You see, this is f of, if you like, this is f of x and y. So use chain rule. Derivative of the outside would be round f round x times derivative of the inside respect to the h would be times the dx dh plus round f round y times derivative of the y respect to the h. Okay, but you know that this is u1 and this is u2. So you have the fact that the g prime of h is equal to the round f round x, okay, times u1. Okay, it's going to be round f round x. You see, it's going to be g prime of h that you have. The difficulty is going to be just a point nobody, and this is going to be round f round y. This is going to be u2. But if you find it at 0 really, because these are going to be the point that you have is x and the y, but if you put h equal to the 0, you see if h is going to be equal to the 0, then h equal to the 0, so x would be x0 and the y would be y0. So basically this means g prime of 0. Okay, so this means g prime of 0, which is equal to the directional derivative that we have, is going to be round f round x at u1 plus round f round y at u2. But remember, g prime of 0 is just G prime of 0 is just the directional derivative. So the directional derivative of f at x0, y0 respect to the u is simply round f round x times u1 plus round f round y times u2. That gives you a very easy formula in order to evaluate the directional derivative of the given function. Okay, so I'm going to make it official, write it down as a theorem for you. And as you can see, it's very easy to operate to get these numbers together. Okay, so what we did is the following. You can, some book, they call it definition, but we call it theorem there because I prove it for you. So the theorem is this one. You use this as a definition. If z equal to the f of x comma y is going to be differentiable in a sense that we talked about it before. It's going to be differentiable on the domain D, then for any unit vector, u, which is equal to the u1 and the u2, you have this. Directional derivative of f at xy in the direction of the u is simply round f round x. Okay, round f round x. Let me write it down as a f sub x. F sub x at x comma y at u1 plus f sub y x comma y at u2. So that gives you the directional derivative. Nice and easy formula to work with. It's the same thing here. So you don't have to worry about, that that is starting. But it would be nice, you see, to just prove it so that you can see the connection between this, and that will help you to understand it when we keep going through this section. So this is the formula that we're going to use for the partial derivatives. For the directional derivative. You make sure to remember u must be a unit vector. So this vector would be given to you anytime you want to find it. First, okay, first check to see if this is going to be a unit vector. If it's going to be a unit vector, you do it right away. If it's not going to be a unit vector, you know that. If it's going to be a unit vector, you can change it to the unit vector. Remember, normalizing the vector. So it's always possible to find it. Are you ready? That's it. We give you one of them on the test just to find it. And this is the way you do it. It would have some advantage for us when we get to the end of the course. And of course, by itself, it's very popular in application problems. So that's it. We give you one question. One of those 6 questions are going to be straightforward directional derivative. 2 types. That's type 1. Find the directional derivative of f. This is the way they ask you. If f of x comma y is equal to simply x cubed minus 3xy xy plus 4y squared, and u is given to you as u is equal to, u is equal to the vector that's given by radical 3/2 I plus 1/2 j. Okay, that is given. And then sometimes they ask an extra question. The extra question is going to be, let me ask you, what is, because they ask x and the y, what is directional derivative at the 1, 2, at the direction of u. When you find it, it's a kind of a function. Then you substitute for these 2 numbers. First thing to do, you check to make sure that this u is a unit vector. Because if it's not going to be unit vector, you have to change it to unit vector yourself. Okay, are you ready? Solution. So this is going to be the case. You check. First thing to do is u is given to you. It's going to be radical 3/2 and 1/2 is a unit vector. That's a claim. Okay, you check it for yourself quickly. Make sure it's all right. You know that norm u squared is going to be radical 3/2 squared plus the 1/2 squared. So radical 3/2 squared would be 3/4, and that would be 1/4. So you get a 4/4, which is 1. So that's fine. It is the unit vector. Now go with the formula. Directional derivative of f at x, y in the direction of the u is simply f sub x times u1 plus f sub y times u2. That's it. Partial derivatives. Partial derivative respect to the x, 3x squared minus 3y. 3x squared minus 3y. That's f sub x. Partial derivative respect to the y. Respect to the y, this would be 0. That's a negative 3y plus 8y. Okay, it's going to be negative 3x. That's a 3xy. So it's going to be negative 3x. Okay, negative 3x plus 8y. That's it. And you already got the u1 and the u2. So the partial derivative respect to this is going to be, okay, f sub x, and this is f sub x, 3x squared minus 3y times u1. u1 is radical 3/2. Okay, and it's going to be plus f sub y, which is a negative 3x plus 8y times u2, which is 1/2. Okay, so that would be a directional derivative in general question. But they ask you only also as 1 and 2. So for 1 and 2, you put the x equal to the 1. So you want to find this is it. So x is equal to 1, y is equal to 2. So you substitute. So this is 1 and 2. Substitute here, and you get your result. X is equal to 1. So it's going to be 3 minus 3y, 3 times 2 times radical 3/2. Okay, plus negative 3x would be negative 3. And the 8 times 2 times 1/2. Just simplify it. So that gives you negative 3 times radical 3/2. And that would be 16, 13. Okay, plus 13 times 1/2. So the final answer is a negative 3 radical 3. Okay, half, and that would be 13/2. Use your calculator or just write it down as a negative 3 radical 3 plus 13/2, the final answer. Okay, so it's not going to be a big deal to find it. So this is going to be a type 1 type that you will see it. Then you can consider it as we did it before. Okay, remember we described the partial derivatives as it's the kind of the slope in the x direction. In the y direction, you can extend it to this one as well. I just give you a remark, but I need the second type of the example. Okay, so let's give you that second type first. So this is where sometimes you missed it. Be careful. Check it first. Okay. Example. Like this. You ask you to find the directional. Okay, find the directional derivative. Okay, directional derivative. Of this function. The function is f of x comma y, which is equal to the x squared, and this is x squared of y. You find the directional derivative of this function at the point. Okay, at the point. The point is a negative 1, 2, and in the direction. Okay, in the direction of this vector, of the vector. So the vector v is 3 and the negative 4. It's going to be a vector. So you check to see if this vector is going to be unit vector. Of course, 9, 3 squared 9, 4 squared 16, 25. The norm is 5. It's not a unit vector. So we're going to normalize it. Normalizing means you divide by the norm. So that gives you the same, almost the same vector. It's going to be unit vector. Okay, it's going to be unit vector, but in the direction of the, okay, in the direction of the given vector. So that would be fine. So make sure don't miss it. You have to normalize it yourself. Okay, so you check to see if this is going to be a unit vector. V equal to the 3 and the negative 4 is a unit vector. Just check. So no, you check the norm V squared. So the norm would be, okay, norm would be 9. That's it, it's going to be 3 squared plus negative 4 squared. So that gives you 9 and the 16, which is equal to the 5, 25. So the norm of the V is going to be equal to the 5. So that answer would be no. So you have to normalize it. Okay, so V is not a unit vector. So normalize V. Normalize V into U. Remember, to normalize it, it's going to be unit vector, which is going to be equal to the V over norm of the V. Norm of the V is 5, so the vector is going to be used. It's going to be 1/5 times V. So 1/5 times V, this is V, multiply a fifth, so it's going to be 3/5 and the negative 4/5. So this is going to be a vector that you're going to use, okay? So U equal to the 3/5 and the negative 4/5 is the one that we're going to use, okay? Is a unit vector. Is a unit vector. Just make sure don't miss it. You should do it yourself. So you check it if you need it, so you do it. So now we know the formula. So go for the partial derivatives again. Okay, so any question? So make sure you normalize it yourself. So bring the function and take the partial derivatives. This is it. The function is f of x, y equal to the x squared over y, which is the same as x squared times 1 over y. So f sub x derivatives, partial derivative with respect to the x, 2x. So that gives you 2xy. Okay, then f sub y. You know that derivative of 1 over y would be negative 1 over y squared. So that gives you negative x squared y. So these are going to be partial derivatives. Okay, directional derivative. So the directional derivative of f at x, y respect to the u is f sub x u1 plus f sub y u2, those partials. Just substitute. F sub x is 2xy, and the u1, of course, is 3/5. And plus a negative x squared over y, u2, which is negative 4/5. So you put them together and you give us the partial derivative. So this is it. So that give you the, okay, so that give you the partial derivative, directional derivative as 6, okay, that's it, 6x on the top, 6x 5y, and this is going to be plus 4x squared over 5y. That's a partial derivative function, but you want it at the point, remember, you want it at the point -1 and -1 and 2. Of course, this is, I made a mistake here. Yes, this is the squared, partial with respect to the y squared, and this is going to be the square, and this is the square. Okay, so that was the, because the derivative of 1 over y is a negative over y squared. Thank you. Okay, but we are not done because we wanted to find at the point, okay, at the point -1 and 2, remember? At the point -1 and 2, then I substitute. You can substitute in advance or you can do it at the end here. Okay, so the question is, you've been asked to find the partial derivative at -1 and 2. So we just substitute and simplify it. So that's it, the partial derivative, 1 and 2. So your x is a -1, y is 2. We substitute, so it's going to be 6 times a -1, and this is going to be 5 times a 2, and it's going to be plus 4, and that's a -1 squared, and that's a 5 times 2 squared. Okay, if we simplify it, this is it. So on the top, you can simplify 6 and the 3. So that gives you -3/5, the first one. And the second one, 2 squared, this would be cancelled out, a 1/5. So a final answer would be -2/5. So that gives you, directional derivative as -2/5. Okay, any question? So it's easy to find. It's for the function of 2 variables. We can extend it to the function of 3 variables. Okay, I just remind you the formula to make sure you know it when we want to use it. Okay, and this is it. We give a couple of remarks and then we try to finish it. So different remarks that we can have. So first one is, if you have a function of 3 variables, it's possible. So if z equal to the, let's call it w, equal to the f of x, y, z is a kind of differentiable in the sense that we have, then we can have a directional derivative. Okay, directional derivative of f at the point x, y, z in the direction of the u is going to be f1 u1 plus f2 u2 plus f3 u3. Okay, where or when u equal to the u1, u2, u3 is a unit vector. Is a unit vector, this time in R3. Okay, and we know that notation of the F1, F2, F3, we used it before. So those partial derivatives. So, you have to in your practice one. So you have the solution. So just check it. Make sure you are familiar with the notation. And again, U must be a unit vector. So if you need it, you are going to change it. So that's going to be one. Any question? The other one is going to be interpretation of this formula. There are going to be two different interpretation of the derivative as we did it for the function of one variable. One of them is the tangent line. The tangent line is as we did it before. We fix one variable. We did fix one variable and we get this slice, we cut it. The same thing here. Just remind you one of them. Okay, so if you like a derivative of the function for the two variables, x0, y0, in the direction of the unit vector can be considered as the slope, or can be considered as the rate of change to solve it. It's very nice application. You will see it can be considered. Okay, as the rate of change. It's very popular in this format. And we are going to, this is your second problem that we have in this section. We're going to describe it in a minute. The third case is the tangent line format. Again, it's possible because it would be at the given point, you just like the one that we did before. See, y was peaks, we just get the slice of the curve with that planes in the direction of the x and the y. We get the tangent line. It's a similar one for this one. So if you like interpretation in two-dimensional is the directional derivative. It can be considered the slope. Can be considered again as the slope of the, you have to cut it, slice it if you like. They call it the slope of the cut edge, the slice, cut edge. Okay, cut edge at the point. Okay, at the point is going to be x0, y0. You put it inside the function in three-dimensional. You are going to have a three-dimensional solid as your graph, and you cut it. Okay, when if you like, we slice, we cut the surface of the solid, the surface z equal to the f of x comma y with the plane, with a vertical plane, with a vertical plane parallel to the, okay, parallel this time to the vector in that direction. Previously, we cut it by the in the direction of the x and the y. Now we do it in the direction of the u. Okay, vertical plane parallel to the vector u, and that plane containing the point, or at the point. Containing the point. Use those softwares that I show you, or just calculator, you see it. Point x0, y0, z0. So it's, interpretations are all possible. So nothing to worry about, but this one is more interesting, and we're going to focus on this. Give you that application problems that we have usually. This is 1, 2. No, there is another one for future, which is much more interesting than the one that we talk about it. And that is this port. You see this product here? This product is a kind of dot product. You see, this interpretation is more interesting for future. What is this one? Look at the formula again. Note that depends on what type of function we have. So the directional derivative of a function of two variables are going to be what? The partial derivative times u1 and the partial derivative with respect to the y times u2. You can write this one as a dot product of two vectors. You see the first vector is f sub x, and the second one is f sub y dot u1, u2. See this one? If you get the dot product, you get the same thing of here. This first one is going to be very popular, and we're going to use it in future. This first one, we're going to call it the grad of the function or the gradient of the function. And this is going to be used quite a lot at the end of the course. Gradient of f. We have a special notation for it. This is it, del of f, gradient of f. So this is simply going to be the gradient of f dot the unit vector u. So this is going to be a short version definition. I'm going to just explain it. The gradient, call it the grad. It's going to be quite used quite a lot at chapter 15 at the end of the course. So the gradient, so we come back to it, of the function f. Remember, is a vector. It's going to be a vector function, if you like. A vector function that's going to be denoted by the gradient of f, del f. And that's defined by, I make it official, defined by the grad of f is simply is the partial derivative of x and the partial derivative of y. In vector form, it's going to be fxi plus fyj. Very important quantity, and you will see quite a lot of it. So therefore, this is another format. So the directional derivative of f at the direction of u is simply gradient of the f as a vector dot, okay, dot u. Of course, if a function is a function of three variables, you get, f sub x sub, x, y, z. Okay, so this is another form that we're going to use quite a lot in future to get to know it for the time being. And there is, of course, one application of this one that we're going to show you in a minute. Okay, any question? So we're focusing on this one to give you that great application of the directional derivative. So first, we have to give one example to find it in this format and to read it in this format. And then we give you that last observation, which is a very good one. Okay, so let's get one example. You have some examples in your book. We want to find the gradient of each function. Find the grad. Okay, gradient of the function. As you know, get to know this formula for the time being. It's a short version that we can use for the time being. Okay, so the first one is fxy is equal to the sine x plus e to the xy. It's like just finding the partial derivatives, really, nothing else. So the gradient of the f is the partial derivative vector of the function. So simply say the solution. Partial derivative with respect to the x, lift up a sine cosine. Exponential function never change. It's going to be e to the xy, but derivative with respect to the x would be y. So that give you y e to the xy. That's f sub x. F sub y, sine x is isolated 0. Exponential function the same with respect to the x, respect to the y would be x. So x e to the xy. So that gives you x e to the xy. So gradient of f is going to be, that's it, fx fy. So in this case, you just repeat these formulas. Cosine x plus y e to the xy, comma, x e to the xy. So that gives you the the gradient of the f. We do quite a lot later, not now. Okay. Give you one with the function of 3 variables. Any question? Just a simplification of the operations so far. Function of 3 variables, just to remind you, this is where you are going to use it for 3 variables in future. So that's x, y, z squared. So the gradient vector would be, okay, the grad of f is going to be partial derivative with respect to the x, partial derivative with respect to the y, and respect to the z. Remember, it's a vector. And you can find it right away here. Okay, the with respect to the x would be y is z squared. Respect to the y would be x z squared. And the with respect to the z would be 2xyz. So that gives you the gradient of the vector, and you're done. Any question? Now, that would take us to the last point about this directional derivative and why we are interested in this type of problems. Because when we talk about derivative of the function, mostly we are interested in maximum and the minimum, a kind of optimization problem. So there are some optimization problems that we can use the idea of the directional derivative. We're going to have another one later on, but this would be interesting. So we are going to go back and look at the definition again to see what we can get. Okay, so I'll give you the last remark of these derivatives, and this remark would be interesting. This is the new notation and why we use this notation. Okay, we want to try to see if we can find the maximum value, for example, of a maximum value or the minimum value or absolute maximum, absolute minimum of this directional derivative. So we may wonder why you need them. You said derivative always is velocity, if you like, that is rate of change. So for example, you want to travel from here to Vegas. So you're going to have different direction to go, and the weather is very hot. So we want to know that you see at which direction, if you like, you may get the maximum hit. So you would like to exactly to pinpoint that direction. So it's going to be used when they want to do the weather forecast, etc. They give you the velocity or the wind velocity at different directions. So they use this type of ideas. Okay, let's see how they use it. So let's go back and look at the formula to see if we can find the maximum values. You see, note that this is the formula for the function of 2 variables. Okay. So as we talk about, it's going to be directional. It's gradient of the f dot u. So you want to find an estimate for this one. Okay, and you want to estimate it. So what we do is we find the absolute value of this. Remember, they are numbers, remember. It's a dot product, it's a number, so this is also a number. So I can talk about the absolute value. So I want to estimate it, so I take the absolute value of the directional velocity. Okay, that's going to be the 1. So that takes me to the absolute value of this one. dot product. Okay. The dot product by itself is a number, but each of these insides are vectors. So I want to estimate it. So I want to see if it's going to be less than something else, if you like. Remember Cauchy-Schwarz inequality or the CBS inequality? What is the Cauchy-Schwarz? Remember the Cauchy-Schwarz CBS, Biankowski and Schwarz? That was the norm of the absolute value of x dot y is less than or equal to the norm of the x, remember, times norm of the y. That's a Cauchy-Schwarz. So we can use the Cauchy-Schwarz inequality here. So if you use the Cauchy-Schwarz inequality, this would be what? This would be less than or equal to the norm of the first vector, which is the gradient vector, times the norm of the second vector, vector u. Okay, so I did this one by applying the Cauchy-Schwarz inequality, CBS. But u is a unit vector, so this is 1. So you see, nicely I find an estimate for the directional derivative. So what I have is the norm, the absolute value of a directional derivative of f at x and y in the direction of the u is always less than or equal to the norm of the gradient vector. You see, norm of the gradient. Remember, the gradient is a vector, but the norm of the gradient vector is a number. So I find a kind of upper bound for the partial derivatives over here. So that gives me a kind of a maximum value. Okay, so that show you that the value of the partial derivatives is going to be always less than or equal to the norm of the gradient vector. So this means the maximum value. You see the maximum value that we can have for that partial derivative in the direction of the u, the maximum value is going to be just the norm of the gradient. So we know if the function is given to nicely, you can find out what's going to be that maximum. Okay, and you may be asked, okay, so maximum, you can find that that's a maximum value. Then they may ask how we are going to get that maximum value. When you travel to Vegas, in which direction will get this maximum? You will get the maximum value at the, you see, maximum value of what? Of a vector gradient. So as a value, the maximum will be norm of the gradient of the f. As the direction, you are going to be in the direction of the vector of the, gradient. So the vector of the gradient would give you the direction, the value or the length of that vector give you the maximum value, which is quite interesting, and it's going to be used, in different applications. So you are going to be questioned, a function would become a directional. Then they ask you, find the maximum value of a directional derivative and tell us in which direction these maximum values would realize, if you like. So you must know it yourself, that the maximum value would be the gradient of the norm of the gradient vector. And the direction is going to be gradient vector. If you would like to get the unit vector, it doesn't matter. You find the gradient vector and then normalize it. So that's a very nice, very important observation, really, of this fact. So I finished this one. I write it down as a theorem for you so you can use it. So what I did easily, I find that so that the maximum value, maximum value of the directional derivative, of the directional derivative is simply norm of the gradient vector. Okay, I make it better. I make it as a theorem. And you know that in this sense, with that directional derivative, we refer to it as a rate of change in the application problem that they use. So anytime they talk about the rate of change, they have to go through this type of ideas. So let me make it official as a formal theorem. Any question? So we have to use the Cauchy-Schwarz inequality here to be able to do it. Okay, so make it official for that second problem on the third. So we give it two problems on this. One of them is a straightforward, finding those, directional derivatives. The other one is a kind of rate of change problem that use this one. So our theorem is, suppose again z equal to the, we stated for the function of two variables, it's going to be the same variables. It's going to be the same, of course, for the function of three variables. Suppose z equal to the f of xy is a differentiable, is going to be a differentiable function. Okay, then the maximum okay, maximum value of the directional, maximum value of the directional derivative, maximum value of direction derivative, okay, derivative of f x y in direction of u, or sometimes in the sense of a problem in your book, they call it, or the greatest rate of change. Same thing. Is going to be the norm of the gradient vector xy. And where are we going to get it? And it occurs, okay, it occurs when u has the direction u has a direction as the gradient, means it's the same thing as a gradient. They are parallel. Vector gradient of f at xy. So basically you find the gradient of the f at that given point. Gradient of the f, the norm of the gradient of the f give you the maximum value, and the gradient of f as a vector give you the direction. If you want to normalize it, get the unit vector, when you find it, you find a unit vector because it's the same, in the same direction that we talk about it. Okay, I can give a break. We come back and should give you a couple of problems on this one first, and then we are done. We come back to the gradient. We quite a lot about it in future, but not now. Any question? So have a break. It's 11:56. We come back around 12:10. Okay, and then we get this one, and then we're done with the directional derivative. Okay, I'll give you two examples. One of them especially is very similar to the problem in your book. It's a kind of application problems and need to be explained. But otherwise, two straightforward questions from this one on the test for Monday. Okay, see you then. Okay, so we're going to continue to give you a couple of examples regarding this type of ideas. You may see it, in applications to see how we are going to apply this theorem. Okay, so basically, if you are interested in maximum value for the directional derivative, you look at the gradient function. Gradient function, and the direction is going to be gradient vector. Okay, so I'm going to give you two examples. We have a couple of problems like this one. There's a point here as how you're going to pick your directional vector for this problem. That's why I picked this one. So this is it. Suppose we have a function. Suppose f of x, comma y is equal to the x e to the y, a function of two variables given. So they ask you two questions. The first part, they ask for the rate of change. So find the rate of change. Okay, rate of change. Find the rate of change of the function of f at the point P is 2 and 0. Now, direction, look at the direction. In the direction is going to be in the direction from point P to the point, okay, to the point Q, like the one that I described at two different points. You want to consider it, okay? So, and there is a second part for this one. I write both cases, then I do it. In the second point, they ask for the maximum. In what direction? Okay, it what the direction? In what direction does the function f, okay, does f have the maximum value of change, the maximum rate of change, Okay, as I talk about it, you may have to decide a different direction that you can go from one point to the other. And then you may be interested in at what direction you can get the maximum rate of change, if you like. It depends what is your function. Okay, what's function? Is a temperature function, dollar function, growth function, rate function. Depends on the on the nature of your function. Then you can answer this type of question, which is going to be very, very interesting. Okay, so to do the first part, you see you have the point P. So the point P is given to you. You need a directional vector. The direction is from P to Q. You see, the point is P, it's a 2 and 0, and then the point Q. So they ask you for the direction from P to Q, or so we go for the direction of PQ. So the PQ would be a vector. So this vector is going to be the vector that we're going to be interested in. Okay. So going from P to Q. So in what direction? This is going to be a directional vector. Okay, so that's one point about this problem. And you know that the points are given to you. You want to find a vector. You have to find the coordinate form of the vector. So your vector is going to be from P to Q. So the difference. So it's going to be a vector. It's going to be 1/2 minus 2. And then this is going to be, sorry, that's a 1/2 and 2, 0, 1/2 and 2. This is 2. Okay, 1/2. So that's going to be 2 minus 0. 2 minus 0. Okay, so that gives me -3/2, -3/2 and 2. So this is the requested direction, if you like. So the direction is going to be this vector, which is going to be -3/2 and 2. But of course, the direction or the unit that you use for the derivative must be a unit vector. So take the norm to see if it is a norm vector. It's not, but you just find the norm because you need it. So take the norm of the v squared, which is going to be negative 3/2 squared plus 2 squared. So then make it to the 9/4 plus 4, which is going to be 1625 over 4. Okay, and you take the square root. So the norm is going to be 5/2. So this is not a unit vector. Okay, so V is not a unit vector. It's not a unit vector. So you have to find a unit vector which is parallel to this one. Okay, same direction. And you know that, normalize it. So if you normalize it, your vector is going to be, so you have to introduce the vector u, which is going to be the v over the norm of the v. Okay, the norm of the v is a 5/2. So it's going to be v over the 5/2, which is going to be 2/5. Okay, 2/5 times v, and this is v. So it's going to be 2/5 times negative 3/2 and 2. You have to take it inside. We take it inside, the first one, 2 and 2 will cancel out, that give a negative 3/5. Okay, and we take it 2 for the second part, that give you 2 times 2, 4. So 4/5. So this is going to be your unit vector. Okay, so now this u is a unit vector. A unit vector. Remember, you have to use the unit vector to find the directional derivatives. Okay, so we provide the vector. Now we are going to get that directional derivative in the direction of this vector. Any question? So that was something extra that you have to do when the direction is given to you. You get the description of the direction, so you have to do the extra job. Now we are ready to give you a directional derivative of this function at the point 2 and 0. Okay, so we are going to be interested in the part 1, we are interested in direction of derivative of the function at the point 2 and 0, and in direction of the u. Okay, you know the formula, you know directional derivative at u is going to be simply partial derivatives. You see it's a gradient times f if dot u, different formula to use. Okay, so use the partial derivatives. Remember your function, just to remind you, the function is the function is x e to the y. So find the partials. So f sub x, derivative with respect to the x, is just 1 e to the y. Okay, f sub y, with respect to the y, the function would be unchanged. Okay, this is it. So the gradient vector is going to be e to the y and x e to the y. Okay, you want to find it at this point at the p equal to the 2, 0. So substitute x equal to 2. So put the x equal to 2, y equal to the 0 to find it. So the gradient would be, this is it. So y is 0, we get e to the 0. E to the 0, x is equal to 2, 2e to the 0. So e to the 0 would be 1, so we get a 1, 2. So this is going to be your gradient vector. Okay, the gradient vector at the point is going to be 1, 2. This is it. Now you have the u function. You see the u vector is negative 3/5 and the 4/5. So get the dot product to get the, so directional derivative at 2, 0 in the direction of the u is going to be the dot product of these two. So it's going to be 1, 2 dot negative 3/5 and the 4/5. You multiply them together to get your result. Okay. So it's equal to the 1 times, the components. -3/5 plus 2 times 4/5. Remember, it's a number, the dot product. So for the first part, we get the -3/5. Okay, and the second part, we get 8/5. Okay, that's going to be the 8/5. So -3 plus 8 will give 5. So you get a 5/5, which is equal to 1. So the directional derivative at the point P of the vector in that direction, it's going to be equal to 1. Okay, so that would give us the first part 1, finding the directional derivative. Any question? So the extra job was just creating that directional vector yourself, and always check, because these operations are valid if you get unit vectors. So if it's not a unit vector, you have to change it. Okay, all ready for the second part? So the second part is, this is one direction. You go from P to Q. We want to know, do we have various directions? We want to know at which direction the rate of change is going to be the maximum. So we would like to give us that maximum value, which is maximum rate of change, and give us the direction, which point, okay, which vector, if you like, give you that one, okay? So we know it already, talk about it, that theorem. So the second part, we know that, note that, according to the proof that we have and the theorem that we talk about it, maximum rate of change is what? Is the norm of the gradient vector. That's it. Norm of the gradient vector and give you the maximum value. Of course, you want it at the point. So you have to find the gradient vector, and then we already got the gradient vector. See the gradient vector at 2 and 0. We already got it here. 1 and 2. Okay, at the point P, we check this one. Okay, remember the point P was 2 and 0. So we already got the gradient vector from the first part, which is 1 and 2. So we check the norm of the gradient vector. So the norm of the gradient vector is going to be 1 squared plus 2 squared, which is going to be radical 5. Is a radical 1 plus 4, which is a radical 5. So the maximum rate of change, okay, so the maximum, okay, maximum rate of change, is going to be a radical 5. At which direction are we going to get this one? So, and it can be done, and it is in the direction of the gradient vector. It is in the direction of the gradient vector, gradient vector. The gradient vector is, okay, at the point 2, 0, it's just 1, 2. In some cases, some people, they go with the unit vector, they normalize this one. Both of them are the same. See, if even you normalize it, but we are interested in the maximum, that direction would be the same, because when you normalize it, it's going to be the same vector, or it's going to be the parallel to this one. So we accept that if you just give us this vector right away. Okay, so you must know it in advance yourself that the maximum value would be the gradient, and the direction is gradient vector. That's it. So we just find it and get it. Any question? So that's a kind of application to give you a better understanding. But if you want to do it in everyday life, this is the next one that I talk about it. Usually the example is going to be temperature example, because the temperature at different places would be different. That's exactly, you can, when you look at the weather forecast, etc. They give you all this information right away. So this is the way they are going to evaluate it or calculate it. Okay, so you have a couple of them in your book. So I just explained this one just to make sure you know what they are talking about. And but just give you something. We're going to ask you really to want to make sure that you know what is the application of this directional derivative, and the idea of the gradient and the maximum one is the one that you must know. Make sure you know it. Okay, so I explained this example from your book. They give you temperature function and you want to drive. You want to think about, in which direction give you the maximum temperature, or okay, then you decide how you're going to travel if you like. It depends of the procedure that you have. So there you are. So suppose a kind of three-dimensional one that we didn't do, so we did this one. So suppose that the temperature function, the temperature at the temperature okay, temperature at a point in general, at the point X, Y, Z in a space. Okay, in a space, three-dimensional. In a space is given by this function, is given by, so this would be temperature function. Temperature T of X, Y, Z is equal to, this is it, we got to be patient, we're gonna have this form, AD, and we have a 1 plus X squared plus 2Y squared plus 3Z squared. Okay, that's your temperature function. So you know it in advance, and you can find, if you have the X, Y, Z of the place that you are going, so you can drop it in and find what's going to be the temperature. So what's going to be the question? I'm just, this temperature is going to be, you have to give it a measure. Okay, which system are you talking about? So when the T is measured, okay, measured in degrees. Okay, Fahrenheit or just those Celsius, centigrade if you like. Okay, and the X, Y, Z, of course, is going to be position in meters. Okay, and X, Y, Z in meters or miles. So that's a function and the units. So what do you want? As we talk about it, you want to travel or you have something in mind. So you have to decide. We want to know in which direction the temperature would be a maximum or would be increases. This is the expression that they ask. In which direction? Okay, in which direction does the temperature? In which direction does the temperature increase? Okay, increase fastest. Fastest at the point 1, 1, -2, you see. So pick a special point that you have in your mind. And then you want to, at that point, get those different direction. You want to know which direction would be harder, okay? And then, of course, they ask you what is the maximum? What is the maximum rate of change? The maximum, okay, maximum rate of change. The change of the temperature. Of the temperature. That's it. You see, it's abstract. It's an application version of the abstract that we talk about it. It's in three-dimensional. You know the answer. You know that the direction is going to be direction of the gradient vector. Vector. The gradient of the function. Okay, gradient vector of the function. your function is t. So you have to find the gradient of the t. So gradient of the t at this point, 1, 1, -2, give you the direction. And the maximum, the norm of the gradient at this point, give you the maximum temperature. You're done. Okay, so if you drop all these, suppose this function is given to you and they ask you to find the gradient of this. Okay, but when you put it in the application version, you must know it yourself, that what is going to be the conclusion. So that's a very nice application of this form. Okay, any question? So we must know that theorem and then go for it. This is it, solution. You know what to do. You know that you have to find the gradient vector. Okay, so you know that you have to find the gradient of this t, if you like, the norm of the gradient of the t at the given point, and the point is 1, 1, -2. Okay, so that's it. So go and find it. You find the gradient and then the norm of the gradient. So if we go for it, the function is a function of 3 variables. So first we go for the finding t of t, okay, which is equal to the partial derivatives, t respect to the x, t respect to the y, t respect to the z. But we want it at this point, at the point 1, 1, -2. So find each one of them, evaluate it at the point, and then come back and do it. And so this is going to be the function. So we can do it all together. They are very much similar. And so make sure that you have enough space. So this is going to be the gradient. So the derivative with respect to the x, we see the derivative of the top bottom would be 0. Bottom top, respect to the x would be 2x times the top. Okay, so I write it down. So the bottom would be minus -2x times the top, which is 80, divided by the bottom squared. Okay, bottom squared would be 1 plus x squared plus 2y squared plus 3z squared, all squared. Okay, and the other are going to be similar. Just use the kind of quotient rule. The derivative of the top bottom would be 0. If the bottom top, if of the bottom, the derivative of the x squared is 2x times the top. So we do the same thing for the other components. Respect to the y, derivative would be just 4y. Everything else is going to be the same. So it's going to be -4y times 80. The bottom one, 1 plus x squared plus 2y squared plus 3z squared, again, all squared. Okay, we go with the third component, z. Derivative of the top bottom would be 0, bottom one, derivative of z would be 6z this time, times the top. So this is going to be -6z times 80, and the bottom is the same, 1 plus x squared plus 2y squared plus 3z squared, all squared. Okay, so this is what you have. Now you want it at this point. So substitute x equal to 1, y equal to the 1, and the z equal to the -2 to get these numbers, because the bottom is going to be all the same. So you want to find this, okay, you want to find the gradient at the 1, 1, -2. So if you substitute, this is it. You see this would be -160x. This would be -320. Okay, y, and this would be minus 48 for 80z. Just substitute the numbers and get it here. -160x, x is equal to 1. So that gives you -160 on the top. Down the bottom, we substitute, it's going to be 1. Okay, it's going to be 1, x squared would be 1. Y is 1, so that gives you 2. Z is 2, 2 squared 4, 4 times 3, 12. So that gives you 12. You square it. So this number is going to be 14, 15, 16. So that gives us 16 squared. So it's going to be 16, and the 16 squared is going to be 256. So that gives it 256. Okay, and then we can simplify it. So that's the first one, and we continue with the others to get the rule. Y is equal to 1, so that would be easy. On the top, we get negative 320, and simplify. The bottom one is 256. Okay, and this next one is Z is equal to negative 2. Negative would be positive. 2 times 480 would be 960. 960, and that would be 256. Okay, I just simplify. I just substitute x equal to 1. Okay, we just substitute x equal to 1. Okay, y equal to the 1, and the z equal to the negative 2. So we simplify 256, and 160 would be simplified by 60. So that gives you 60, and that gives you a negative 10. Okay, so if you do all this simplification, so this is what you are going to get. So the gradient vector at 1, 1, and negative 2 is going to be, so we have a negative 10 and the 60. I simplified by 2, so that gives negative 58. So this would be negative 58, the first one, comma. And we can simplify this by 16 again. Even by 32, we can simplify it. By 32, that gives you 8. So that gives you 8. And the top would be negative 10. Then I simplify it again. And I simplify the last one. That gives you 30 over 8. Okay, that's one. You can simplify it, or I just pull out the 58. And I write it down as 58, just option, option not. Negative 1, negative 2, and 6. Okay, different version to write it down. All of them would be the same. Okay, or just the inside one. So and now this is it, the gradient vector. And now, if you want to get the direction, there's going to be direction of this vector. You can pick this vector, or even you can pick this one. It doesn't matter. All of them are going to be the same. And even you can find the unit vector. Then you are going to find the norm, of course, the norm in order to get the maximum. So get the norm. So it's going to be the norm of this vector. Okay, you have to go with the norm of the actual one. So if you take the norm, you know that you have to square each one of them. So basically, this is going to be, you can pick the 58, and then the square root of these squares is going to be 1 plus 4 plus 36. So that gives you 40. So it's going to be 5 over 80, a square root of 41. Use your calculator, that should give around 4. So it's going to be a kind of 4 degrees. Now, you know that this is going to be the maximum temperature as we talk about it. So the maximum temperature that would be increases at this, okay? So the direction is going to be the direction of this vector. So we can pick this one if you like. And the maximum rate of change, or the maximum temperature, is going to be 4 degrees. So I'm going to just write explanation for it, but otherwise be done. Okay, so the maximum, this is going to be the maximum. This is the maximum. Okay, maximum rate of change. Rate of change. Rate of change of the temperature, okay, of T. That's going to have. So this is going to be the maximum rate of change. The direction is going to be the direction of the gradient vector. The gradient vector, it doesn't matter. You can pick all of them, or you can pick this one, or you can normalize it. All of them are going to be the same and the same thing. Okay, so I have to explain it. Are you done with this one? So as you can see, it's a nice application. So all the result is just a single operation, but you have to know to explain it nicely. So let me just explain it, what we have. That is going to be you are fine, if you write that one, you're fine, but I want to explain it so that you have it. So this is it. You can say that the temperature, okay, the temperature increases fastest, if you like, fastest in the direction of the gradient vector T, or equivalent, if you like, equivalent or equivalently, if you like, in the direction of this vector, of the vector -1, -2, 6. Okay, I just drop that 5, 8, because you know that they are going to be parallel. Even if you want to get the unit vector, you see if you want the unit or the unit vector, but that would be fine for us. The unit vector, you know that the norm of that vector was 1/41. But we're happy with the first one. Okay, so that gives the directional vector, and the maximum rate of change is, as we talk about it, the maximum rate of change of the temperature is 4 degrees. And then, okay, kind of very nice application really of what we did over there. So we create a situation and we give you one of them on the test because it's a great results. So we want to check it. So expect 2 problems from the directional derivative on the test, and you already got the sample. Just check it. One of them would be straightforward. You just find it for us. And the other one would be of this type of ideas. So when you find it, you have to explain it because they are going to ask for the maximum rate of change. Maximum rate of change, you must know it, that the maximum rate of change is just the norm of the gradient vector and the direction that you are going to get that one. And you're going to get the direction that would be the same as the direction of the gradient vector. So you find the gradient vector, it's a bonus. That give you the norm of that vector, give you the maximum rate of change, and the vector itself give you the direction. So that is making sense. Very nice application. Okay, that's it. We're done with 13.6, which is directional derivatives. So we give you enough different interpretation of the derivative of the function really nicely. So you have 2 different interpretation in function of 1 variable, tangent line interpretation and the rate of change. So we give you both of them. Okay, the one that we did the other day was the kind of, we stay with the tangent line and we apply the linear approximations, which is the tangent line approximation in calculus 1. And we extend it to the function of several variables. Today we give you directional derivatives. You can consider this one as a rate of change problem or consider it as an extension of the partial derivatives. We would have many applications in physics. We come back to it in chapter 15. And we work quite a lot with the gradient, of course, most of the time. Okay, so that would be section 13.6. Now, I'm going to give some idea with 13.7. 13.7 is an easy section. We already talked about it a little bit. In your book, they bring this one up here. They talk about tangent planes. Okay, so we already talked about this tangent line interpretation that we have, L of xy, as I talked about the other day. we approximated with the tangent plane really. So the advantage of this section is going to be they focus once more of finding these tangent planes to the surfaces. Especially you are going to have your surfaces, of course, the function is going to function of 3 variables. So the situation is the same really. You remember L of xy is what? F of a, b, partial derivative of f times x minus x0, and the partial derivative of y times y minus y0, exactly like the one that we did. So this procedure would end up the same thing. But since it's going to be towards the surfaces, that give you a nice geometrical interpretation of the idea. So it's easy case, and you already got it, one formula. And we give one question of this one on this, okay, on this coming test, okay? So we can do it quickly, 13.7. It's very a standard argument. But it's nice to construct. I can give you the formula right away, really, one formula. And you know it. You see, let me just, but I would like to give you interpretation nicely, a little bit geometry, and then the formula. There you are, tangent plane. So we get one direct question of this one. I would like you to write the equation of a tangent plane for us. What is tangent planes? But this time, you know, they call it level surfaces. That's a new expressions. Level surfaces mean a family of surfaces, if you like. I'm going to explain it. What does it mean? Level surfaces. Okay, let's see what you know. You already know the tangent line approximation is just a tangent plane. So let's, what you know so far, recall that. You see, all we do, we just extend. Recall that if you have a function of 2 variables, you see, Lxy, remember that tangent line approximation, you can use the tangent line approximation as a tangent line, okay, or linear approximation. So if this function, if is differentiable, we talk about it, that the function can be approximated by its tangent line. In this case, tangent plane is differentiable, then the equation of the tangent plane to the surface, to the graph, surface z equal to the f of x comma y at the point x0, y0 is given by, that's it. Given by what? You see, it was, remember, it was L of xy equal to the value of the function. We change it a little bit. It's going to be z minus z naught. Sorry. Equal to the partial derivative respect to the x at x0, y0 times x minus x0 plus the partial derivative of y respect to the y times y minus y0. See, that give you the plane. You know that this is z0, you know, I just can note that. You see, z0 means f of x0, y0. If you substitute on the over there, that simply give you the equation that you are familiar with. You see, that gives you z equal to this is just tangent line approximation. You move it to the other side, and this is it. It's the one you did before, but you call it the linear approximation. y0, y minus y0. You see, that's the one that you know for 2-dimensional. So what we'd like to do, we would like to change this one into the three-dimensional format. Okay, so with the function, they call it level surfaces. So what's going to be in the case of the level surfaces? Okay, now in general, extension of this formula when the function is a function of three variables. In general, extension is nice to get the formula. Suppose S is a surface. S is a surface with the equation, a kind of implicit one. This is the equation. F of X, Y, Z, let's say equal to the K. Okay, so there is a Z, but Z is inside here. Okay, in the other one, you just find it straightforward, Z equal to the F of X, Y, to get the numbers. If this is going to be the case, where K is a constant. K is a constant. Okay, that is going to be the case. If you want an example, for example, if you get, ellipsoid, if you get a sphere, you get x squared plus y squared plus z squared equal to 1. X squared plus y squared plus z squared equal to the 5. If you have ellipsoid, you know that this is going to be what? 4x squared, 9y squared, 7. So z is around here inside. If this is going to be the case, the expression is S, that surface is referred to it as a level surface. So then S is going to be called, okay, it's called a level surface. Level surface of the function, of that function, f of x, y, z, of three variables. Okay, that's it. That's the argument that we have. So if you can solve it for z, you see, if you can solve it for z, this gives you your tangent plane. So if it's going to be combined together over here, like the ellipsoid, sphere, okay, all those quadratic form that we talk about it. Yeah, okay. So what we'd like to do, we'd like to see what's going to be the notion of what's going to be the equation of a tangent plane for this type of graphs. Okay, now the way we're going to do it's going to be a similar one. We end up with this. You know that if you want to write the equation of a plane, what do you need? You need a point and you need a normal vector to be able to do it. The point would be given to you. They're going to ask you to find it, point P. So the question is going to be, what is the normal vector? So a normal vector, you need a point. Okay, you need a vector that give you the normal vector. So what I'm going to prove for you is something interesting. I'm going to prove for you that for this type of graph, okay, that normal vector that you are looking for is what? Is the gradient vector. And what is the gradient vector? The gradient vector is what? F sub x, F sub y, F sub z. So when you want to write the equation of a tangent plane, that gives you your vector A, B, C, remember? So what is going to be now the equation of a plane? Remember, A times x minus x0 plus B times y minus y0 plus C times z minus z0 equal to 0. That gives you the equation of the plane. Okay, that's the idea. Okay, any question? So let's see how we're going to arrive at the gradient for this one. It's quite interesting. So the problem is going to be, so we pick a point. The point would be given to you, okay? So I want to define that tangent plane and relate it to the normal vector. So I have to define that tangent plane first. So suppose you have a point. Suppose P is a point, given point, x0, y0, z0, that would be given. is going to be on S. Remember, S is a surface. And C, remember the way we talk about the tangent. We cut it, if you like, and C is any curve. Is any curve, okay, that lies on S, passes through, okay, passes through the point P, through the point, okay, the point P. So it's like, your graph is going to be, your solid is going to be kind of ellipsoid, okay, or going to be kind of a sphere. Then you fix the point P on it, okay. Then you are going to cut it, if you like, slice it, touch it. A curve C, you pick a curve C on that solid that you have. Okay, this is going to be the curve C. That you pick that curve on your ellipsoid, for example. But this curve passing through the point P that you would like to find the tangent plane, if you like. Okay, that's going to be the case. Now we are going to work on this one to get that gradient that we talk about. We have to describe it. So this curve with an equation. So assume that R of t as usual, which is going to be equal to the x of t, y of t, z of t, is going to be the equation of the curve, is the equation of the curve, okay, the curve C. And it's passing through the point P. So suppose it's passed at this point. When t is equal to the t0, so this is going to be equal to the x0, y0, z0. Okay, it's passing through the point P. So P is going to be satisfied on this one. Now, you know that the C is going to be in S. So the equation must satisfy. And so we should have okay, it satisfied that equation that you have. Okay, satisfy the equation. So you have the f of x, y, z equal to the k. So that would imply that f of x of t, y of t, z of t must be equal to what? Must be equal to the k. Because c is in the, going to be, okay, it's going to be in S. So that equation must satisfy. Okay, now this is what we got over here. Now differentiate both sides respect to the t. Remember, I am looking for a normal vector. And I'm going to show you in a minute that normal vector is going to be. So this is a situation that I have. You see so far, this is going to be C, and this is the point P. So I get a tangent line over here. Okay, so what I would like to do is I would like to get the normal line. So I'm going to prove for you that this normal line is going to be, okay, the gradient of the f. And then that gives me a normal for the, okay. So what I'm going to do, differentiate both sides, respect to the t, use the chain rule, differentiate. You will see when you differentiate it, of course, differentiate respect to the t with respect to the time t. You see, you know that the chain rule, outside, inside. If of the outside, round f round x times dx dt, round f round y, round f, let's just do it. So if you apply the chain rule, it's nice, to take a little bit, a few minutes to prove it. So if you differentiate, this is what you get. Round f round x, because it's a function of x, but times dx dt, chain rule, outside, inside, is a function of y, round f round y, times derivative of the inside, dy dt, plus round f round z, times dz dt. and derivative of the other side is 0. That's it. Write it down in vector form. You see, this is, remember, this is f sub x, f sub y, f sub z. If you write it in vector form, it's going to be f sub x, comma, f sub y, comma, f sub z. That's a vector, dot the other one. What's the other one? The other one is simply x prime of t, y prime of t, z prime of t equal to 0. Okay, this is the gradient. Okay, so this is going to be simply the gradient of f. Okay, this is going to be the gradient of the f. And this is simply, remember the equation of the curve was R3, R prime of t. So this simply give you the gradient of the f dot R prime of t equal to the 0. You know that if the product of two vectors come to be 0, so this means these vectors are perpendicular to each other. So this simply means the gradient of the f at the point x0, y0, z0 is perpendicular to what? To the R prime of t. Remember the R prime of t is going to be tangent line, if you like, the tangent vector. So this means the gradient is going to be the normal vector that you're going to be interested in. Okay, so this means the gradient. So I proved it. So this means the gradient vector is orthogonal. Is orthogonal to the, okay, to the tangent vector. Tangent vector, tangent vector, R prime of T0, if you like. Okay, because this is happening at T0, of course, at the given point. Okay, so this is it. So if we consider so if f of x, okay, if the gradient, of course, the gradient vector, if the gradient of the function is not going to be equal to 0, then it can be considered, okay, so the tangent, okay, so then the tangent plane, okay, the tangent plane of the level surface, that's given to you, level surface of the function f of x, y, z at the point at p equal to the x0, y0, z0 is going to be a plane with a normal vector, is the plane with the normal vector, gradient. You see, this is going to be your normal vector, normal. You know that the normal vector, we usually write it down as A, B, C, remember? This is the way we write it down. So the equation of the normal plane, the equation of the normal plane, of the tangent plane, tangent plane is, okay, remember the way we write it down is A times x minus x0 plus B times y minus y0 plus C times z minus z0 equal to the 0. Or in the language of the one that you have over here, is going to be f sub x times x minus x0 plus f sub y times y minus y0 plus f sub z times z minus z0 equal to the 0. And I extend the original formula that we have. Very nice argument. And you will see the role of the gradient. Okay, that the gradient is going to be just a normal vector over here that you get it. And there is another thing that they use normal line. If you want to find the equation of that line, you know that the normal line would have a direction of the normal vector. And at the point, you see, sometimes we ask for it, the equation of the normal line. Sometimes they ask for it in your book. Normal line, it's going to be, remember, symmetric equation, x minus x0 over a, which is f sub x, equal to the y minus y0 over f sub y, equal to the z minus z0 over f sub z. So that gives you the equation of normal line. That gives you the equation of the tangent plane. That is all you do in this, in this section. So you have to know the idea, the formula, but otherwise it's straightforward because the function would be given to you. So it's quickly you find the gradient of the function and all this argument, and you will get it right away. But you have to know it in advance. Okay, so the difference between this idea and the previous one is, in the previous one, z was given to z equal to the f of xy straight on. Okay, kind of explicitly defined, and use the tangent line version, tangent line approximation to get the tangent plane. But this one is kind of implicitly defined, if you like. You fix, you mix it into the x, y, z, and you have it all for those quadratic, those surfaces, like the conic section that we did have in three-dimensional, and it's going to be applied over there. So it's a straightforward problem and nothing to worry about. I should give you one example. Any question? So one question of this one on the test, and I think you have 2 or 1 on that practice one that I posted, and you get 1 on the practice one. Just check it. It's very straightforward problem. So make sure that if they ask you for tangent plane and the normal line, you have to give us both of them. Okay, this is symmetric equation of a line. Okay, you know that x minus x0 over a over b over c, and you already got the ABC. Because your ABC is going to be your gradient vector. So put them together and get the result and get your points. Okay, but make sure you bring those formulas because you need it, the formulas. Okay, any questions? So the example, straightforward example is going to be the following. Example. So from the argument that we did today, 3 problems for that. You already got 5 questions from your previous quiz. So we get 3 problems over here, it will be 8. We need 2 more. And we talk about it tomorrow. It's optimization problem, something very much straightforward like you did in calculus 1. Find the critical values. There is something we call a second derivative test, and just, straightforward. So we be able to finish this chapter right away. And we test it on test number 2. And as soon as you come back on Monday, you start the nice part of your course. We start integration, and we are not going to use this idea of the derivatives directly anymore. But we come back to the gradient at the end of the course. Okay, the example is this one, straightforward. They give you something like ellipsoid or just, a sphere. These are the candidates for this one. Find the equation. So it's easy question, don't miss it. Find the equation of the tangent plane. So remember, if the equation is explicitly given to you, just use the tangent line approximation format. But it's going to be 3-dimensional, this is the one. Okay, and if it's going to be in level surfaces, if you like. So find the equation of a tangent plane and normal line, both of them. Normal line at the point, they give it the point and the surface. At the point. Point is -2, 1, 3 to the ellipsoid. To the ellipsoid. Okay, that's it, ellipsoid. This is your ellipsoid. X squared over 4, okay, plus y squared plus z squared over 9 equal to 3. That's it. So you can take this one to be your function. Okay, that's it. In your book, even they bring the -3 to the other side and they call it that function, but it will be fine. We call this one f of x, y, z, and we work on this one. Because we differentiate and derivative would be 0, nothing to worry about. Okay, so the solution is going to be, remember you identify the point that you have. So this is going to be the point, and you identify your function f of x, y, z is equal to the x squared over 4 plus y squared plus z squared over 9. Again, you can bring the -3 or no, because we differentiate it, doesn't matter. So go for it. You know that. You need to find the normal vector. The normal vector is going to be the gradient. Okay, so what you have to find is this one. You have to find the gradient of the f. Okay, gradient of the f at these points, -2, 1, 3. So that would be your normal vector. Okay, so you have a point and normal vector, then you can write the equation of a tangent plane and you're done. Okay, so we go for it. For the gradient, you need the partial derivatives. So take each partial derivatives. Say I'll give you the formula. Let's say this is going to be your formula. So you have to find the partial derivative of each and evaluate it at each point. Just to remind you. This is going to be your job. So get them one by one. This is your function. So I go with this f sub x first. With respect to the x, that give me 2x over 4. Everything else would be 0, so that give me x half. I find it at this point, so I need f sub x at -2, 1, 3. X is a -2, so that give me equal to the -2 over 2, which is a -1. It's the first one. Any question? Go on, get the other two. F sub y. With respect to the y, 2y, everything else would be 0. 2y. So it's going to be 2 times y. Oh, I'm sorry, I just go to the formula. So that's going to be f sub y. So I'm going to find the f sub y of -2, 1, 3. So y is 1. So that gives me 2. Now we can find it right away. The way you write it down is not important. Okay, then go for the f sub z. With respect to the z, 2z9. So that gives me 2z over 9. Okay, so evaluate it at -2, 1, 3. Z equal to 3. So that gives you 2 times 3 over 9, which is going to be 2/3. Z is 3 or, okay, we stay with the 3. Okay, everything here is correct. Yes. So we simplify it, that gives us a 2/3. So there you are. We have the gradient vector. Okay, so the gradient vector at the -2, 1, and 3 is simply There you are. We get the negative 1, 2, and 2/3. That's it. So that's going to be a vector, and you already got the point. So what's the point? The point is negative 2, 1, 3. Remember, this is going to be your x0, y0, z0. Equation of the plane, it's going to be a times x minus, what different version. This is the version I write. And this is going to be whichever you like. You can do it right away. There you are. A, this is your A. So this is ABC. Or the formula right away. Okay, so my A is a negative 1, so it's going to be negative 1 times x minus x0, which is a negative 2, so negative 2. B is 2, it's going to be 2 times y minus y0, which is 1. Plus C is 2/3. Okay, 2/3 times z minus z0, which is 3, equal to the 0. You have to simplify it, you know that. So that gives you x plus 2. Okay, that's going to be x plus 2. So multiply the negative 1, it's going to be negative x minus 2. This is going to be 2y minus 2. And that would be 2/3 z minus 2 equal to the 0. We can just multiply inside. So what else we can do is going to be a negative x plus 2y plus 2/3 z. Then you simplify the numbers. So the negative 2, negative 2, negative 2, that gives you negative 6. So that gives you negative 6 and is equal to the 0. That's it. This is your tangent plane. Okay, tangent plane equation. Any question? Normal line, you know that's a normal line is the equation of that line with the in the direction of the gradient. Okay, the equation of a normal line is the line passing through the, it's going to be x over x0 over a, y minus y0 over b, z minus 0 over c. And you already got all the information that you need. So x minus x0, x plus 2, this is the one that you got over here, x plus 2 over a, which is a negative 1, equal to, it's a y minus y0, which is y minus 1, over b, which is 2, is equal to the z minus z naught, which is 3, over the c, which is a 2/3. So that gives you the symmetric equation of the, okay, symmetric equation of that line, and then you're done. Okay, so again, it's not a difficult problem, but just make sure to get those formulas all right to get it through. It's kind of approximately, just extension of the writing the equation of a tangent line is function of 2 variables. Okay, so you get one of them. So you already got one to practice to get this through. Okay, any question? So it's done. This is section 13.7. Okay, so we go to the 13.8 is just relative maximum, relative minimum that you did, okay, for the ordinary function, a function of one variable in calculus 1, and we just extended over here. And I think I'll talk about it tomorrow. The procedure is the same. Remember, if a function of one variable is given to you, you have that famous, you can have a relative maximum, relative minimum, absolute maximum, absolute minimum. Since your functions are real values, means the range are numbers, so it makes sense to talk about it. It makes sense because you compare them together. Because if you have the vector, you cannot compare them together. So no problem. So we can carry on and talk about it as we did it in calculus 1. So we have to define what's going to be relative minimum, relative maximum. Relative minimum is smallest value of the function in a neighborhood. Absolute minimum on the entire domain. So that's going to be the one. Then in calculus, a function of one variable, there are two places that you can get the tangent. You can get the max and the mean, relative max minimum. The places when the lines are horizontal or vertical. When the lines are horizontal derivative is 0. When it's a vertical derivative, does not exist. So those points are going to be called critical values, or the critical points in values or numbers in calculus 1. We do the same thing over here. Then you have the Fermat theorem that if you have a max and the mean, then the derivative must be 0. And then you did have something, we call it first derivative test and the second derivative test. First derivative test is complicated, not complicated, it's not nice. You can do it with the directional derivative, but the second one is easy. So we talk about the second one. I'll talk about both of them tomorrow. There are another method that we can use, this max and minimum. That method really can be done by, you have different softwares you can do it. We call it method of Lagrange multipliers. So it's not a difficult method, but it's messy, especially if the function is a function of 3 variables. So what I do, I just give you one special case, function of 2 variables. You get the idea. You're not going to use it. But if you are going to be some measures, okay, in future discipline, like engineering, you may have to do it numerically, and you have your computer and your calculator that will give you, you can do it. But I give you the idea. So that make it 2 problems, 2 more, so that we'll be able to finish, okay? We'd like to finish this chapter really, because we need all the times that we have for taking care of chapter 14 and the 15, okay? So we do this one tomorrow. And then I already posted the practice test for you and the solution, and I may get a chance to do a couple of them for you. So that's it for today. So tomorrow, section 13.8 and the 13.9, and I finish it. You should be able to do all the problems on that practice when they're posted. Just check at the solution, at least the topics that we did today. I grade your quiz to see what's going on. I do it today. I post it tonight. So if you have making a mistake on that one, you are going to check it. The topics from the quiz are going to be exactly the same thing. Okay, so check those. Okay, that's it. Have a good one. And if you need anything, let me know. Okay, and make your appointment. You know that without the appointment, you won't be able to take that one. So make your appointment. Okay, have a good one. See you tomorrow. Don't miss it. Okay, have a good one. Bye-bye.